So today we're going to be doing Feb March 2023, paper 12. Question number 1 says, 4 equations representing reactions of nitrogen or one of its compounds are given. Which equation represents a disproportionation reaction? You guys might remember that a disproportionation reaction is a reaction in which a single species undergoes both oxidation and reduction simultaneously, right? An atom of a particular element, right, or atoms of a particular element in a single species undergo both oxidation and reduction. Now, reaction 1 is not a redox reaction at all, right? It's not a redox reaction at all because over here, the oxidation numbers of none of the species are changing, right? Hydrogen is +1, nitrogen is +5 in the nitrate ion, right? And it's +5 over here in HNO3. Again, HNO3 is just H plus and NO3 minus. You can think of it that way, right? Calcium remains +2. Carbon is +4, oxygen is -2. Okay, so all the oxidation numbers are the same in the reactants and the products. Reaction B is a redox reaction, but it's not disproportionation. Nitrogen is going from 0 to -3. Hydrogen is going from 0 to +1. So this is a redox reaction, but not disproportionation. Reaction C is just a acid-base reaction, right? Ammonium is acidic, reacting with sodium hydroxide to form ammonia, sodium chloride, and water. Again, this is not a redox reaction, right? Which leaves us with option D as the answer. Over here, the nitrogen is undergoing disproportionation, right? Nitrogen dioxide. The nitrogen goes from +4 in nitrogen dioxide to +5 in nitric acid and +3 in nitrous acid. Okay, you can calculate this also. Oxygen is -2, so you have 2 times -2 for the 2 oxygens. The nitrogen is +4. Here, nitrate ion is -1, H is +1, right? So +1, and then 3 oxygens -2. 3 times -2, so that's +1 minus 6, that's -5. So the nitrogen must be +5. And then here you have +1 minus 2 times 2, right? Again, you have 2 times -2 here, so 1 minus 4 is -3. I mean, nitrogen is +3. So here, this is a disproportionation reaction, right? Some of the nitrogen atoms in nitrogen dioxide are undergoing oxidation, and some of them are undergoing reduction. The diagram shows the Boltzmann distribution for 1 mole of a gas. The gas takes part in a reaction with an activation energy EA. Which statement correctly describes the effect of an increase in temperature? Now, when we increase the temperature, right, what we're doing is we're increasing the average kinetic energy of the molecules, which means that the curve shifts to the right. Okay, the curve shifts to the right. And what that means is that now more molecules have energy greater than the activation energy. So initially it was only these molecules that have enough energy to react, right? But when we increase the temperature, right, what happens is that the curve shifts to the right. More molecules have energy greater than the activation energy, and therefore the rate of the reaction increases, right? And since the curve shifts to the right, it becomes flatter, right? Fewer molecules have energy less than the activation energy, and more molecules have energy greater than the activation energy. The total number of molecules remains the same, right? The area represents the number of molecules. Okay, so over here we can say that peak P will be lower, right? Peak P will be lower, it will be further to the right, and more molecules will have energy greater than the activation energy. A student carries out 4 experiments to investigate the rate of a reaction between 3 grams of calcium carbonate and hydrochloric acid. In experiment 1, we have calcium carbonate powder and 2 mole per dm cube HCl at 35 degrees Celsius. In experiment 2, we have calcium carbonate powder again and 2 mole per dm cube HCl at 35 degrees Celsius. In experiment 3, we have large chips of calcium carbonate, 1 mole per dm cube HCl at room temperature. And in experiment 4, again we have the large chips of calcium carbonate, but now the HCl is 1 mole per dm cube at 35 degrees Celsius. The student collects the carbon dioxide and times how long it takes to produce the same volume of gas for each experiment. What would be the correct times for the 4 experiments? Now in experiments 1 and 2, we're using calcium carbonate powder, which means that the solid has a greater surface area. Solid has a greater surface area in these cases, right? And we're using 2 mole per dm cube HCl. So we have a higher concentration. We have a higher concentration of HCl as well in experiments 1 and 2 compared to 3 and 4. So experiments 1 and 2, okay, will take the lowest amount of time, right? These experiments, or the rate of production of carbon dioxide, will be the fastest in these two experiments. Okay, fastest rate, right? Higher surface area, higher concentration means faster rate. And then the greatest amount of time will be taken in experiment 3, right? Greatest amount of time will be taken in experiment 3. Why? Because we're using larger pieces of calcium carbonate, so lower surface area and a lower concentration of hydrochloric acid, and at room temperature, right? So the temperature is also lower here. So this is 25 degrees Celsius as opposed to 35 degrees Celsius. So this will take the greatest amount of time. The reaction will happen the slowest. Okay, so the rate of production will be the slowest in experiment 3. So experiments 1 and 2 should be the fastest, whereas experiment 3 should be the slowest, which means that the answer is B. Okay, the answer is B. Experiments 1 and 2 take the least amount of time. Experiment 3 takes the most amount of time, and then experiment 4 is somewhere in between, right? We're using larger pieces and a lower concentration, but the same temperature as the first two. Okay, so it will be in between. So the answer is B. The table shows the partial pressures in an equilibrium mixture formed by the Haber process. What is the numerical value of the equilibrium constant Kp for this reaction? Now for the Kp, we're just going to take the partial pressure of the products. In this case, that's ammonia, to the power of its stoichiometric coefficient, partial pressure of ammonia squared to the power of 2, right? And then we're going to divide that by the partial pressures of the reactants, the product of the partial pressures. We have partial pressure of hydrogen cube, right, because the coefficient is 3, times the partial pressure of nitrogen to the power of 1. And then this is equal to 4,000 squared, that's the partial pressure of ammonia squared, divided by 8,000 cube for hydrogen, times 7,000 for ammonia. This gives us a value of 4.46 into 10 to the power of negative 9. And the units here, we have pressure squared in the numerator and pressure to the power of 4 in the denominator. Okay, we have pressure squared divided by pressure to the power of 4. That's 1 over P squared. In other words, that's just pressure to the power of negative 2. So the units here will be kilopascals to the power of negative 2. The answer here is A, 4.46 into 10 to the power of negative 9 kilopascals to the power of negative 2. A reversible reaction is shown. Which change in conditions will move the position of equilibrium to the right? Move the position of equilibrium to the right and increase the value of the equilibrium constant. Now this reaction here that they've shown, right, the forward reaction is an endothermic reaction. It's an endothermic reaction because delta H is positive, and an increase in temperature favors endothermic reactions. Okay, remember, if you want to change the value of the equilibrium constant, the only factor that affects the value of the equilibrium constant is temperature. Okay, the only factor that affects the value of the equilibrium constant is temperature, and if you want to increase it, we want to move this equilibrium to the right for an endothermic reaction, right? The forward reaction is endothermic. An increase in temperature will favor the endothermic direction. So if we increase the temperature, the equilibrium will move to the right and the equilibrium constant will increase. So the answer is D. The ore silomelane may be considered to have the general formula Ba MnX plus Mny plus 8 O16 OH4. In this general formula, X plus and Y plus are two different oxidation states of manganese and silomelane. What could be the values of X and Y? Now to do this, okay, we first need to figure out what the overall charge of all of these manganese ions would be. Okay, in this compound, we have manganese in two different oxidation states in this compound, right? We know that the overall oxidation number of the compound is 0, right? It's a neutral compound. Now barium is plus 2. Barium is plus 2. We have 1 manganese with an oxidation state of plus X. Okay, so we have plus X here. We have 8 manganese with an oxidation state of Y, right? So we have 8 times Y plus 8 times Y. Then we have 16 oxygens, right? Oxygen will be negative 2. And then we have 4 OHs, right? 4 hydroxides. And we know hydroxide is just negative 1, right? We have 4 times negative 1 here. And the overall oxidation number is 0, okay? So then what we get is, we get X plus 8Y as the overall oxidation number of all the manganeses in this compound. And that is equal to 2 plus 16 times negative 2. So that would be, we have 2 minus 32, that's negative 30, and then we have negative 34. So we have X plus 8Y minus 34 is equal to 0. That means X plus 8Y is equal to positive 34. Now which combination gives us that? If we take the first guy, when X is positive 2, and X is positive 2 and Y is positive 4, we get plus 2 plus 4 times positive 8, and that gives us positive 34. So the answer is A. The overall oxidation number of all the manganese atoms in this compound comes out to positive 34 for option A. Silicon reacts with a mixture of calcium oxide and magnesium oxide at 1200 degrees Celsius. Which statement about this reaction is correct? Now each of the options has to do with what is being reduced and what is being oxidized. So just looking at the equation, right, we can clearly see that magnesium is going from magnesium oxide, so it's plus 2 over here, to its elemental form, so 0. So magnesium is being reduced, which leaves us with options B and C, right? A and D are incorrect. And then we look at silicon here. Silicon is 0, and the product, we have 2 calciums, which is 2 times plus 2, and we have 4 oxygens, that's 4 times negative 2. Let's say silicon is X, right? So we have X plus 4 for the 2 calciums minus 8 for the 2 oxygens, right? And the overall oxidation number then is positive 4. So silicon is being oxidized from 0 to plus 4. Okay, silicon is being oxidized from 0 to plus 4. So magnesium is reduced and calcium is neither oxidized nor reduced, right? Calcium remains positive 2 in the reactants as well as the products, okay? Silicon is being oxidized. So it's incorrect to say that silicon is neither oxidized nor reduced, okay? Silicon is oxidized, so the answer is B. Magnesium is reduced and calcium is not oxidized or reduced. In which species is there a lone pair of electrons? Now over here we have CH3, that's a methyl radical. We have CH3 plus, that's a cation. We have CH3 minus, and we have CH4. So let's look at CH3 for a second. Right now, carbon has 4 valence electrons. Okay, carbon has 4 valence electrons. Now in CH3, carbon is making 3 single bonds, right, with hydrogens. So CH3 radicals don't have a lone pair. CH3 plus, this electron is removed, so it doesn't have a lone pair either. CH3 minus, there's an additional electron on the carbon, which gives it a lone pair, right? So this is CH3 minus, and CH3 minus has a lone pair. And then obviously CH4 doesn't have a lone pair, right? Because carbon is just making 4 single bonds in that case. Under which conditions will nitrogen behave most like an ideal gas? Now for a gas to behave ideally, what you want is the gas to occupy a very, very large volume. Okay, you want the gas to occupy a very, very large volume. The reason why is because this will minimize the intermolecular forces between the particles because they're going to be far apart, right? And it also means that the volume of the particles themselves, or the atoms or the molecules themselves, is negligible compared to the volume that the gas occupies, right? These are both ideal gas assumptions. So at a high temperature and a low pressure, gases occupy the greatest volume. So therefore the answer is B. The higher the temperature, the lower the pressure, the more ideally a gas behaves, okay? Because the larger the volume they occupy, the weaker the intermolecular forces, and the smaller the particles relative to the volume occupied. The equation for a chemical reaction is shown. All substances are in their standard states. Which statement describes the standard enthalpy change of reaction for this reaction? The enthalpy change when a total of 1 mole of products is produced, well, in this case, we are not producing a total of 1 mole of products, right? Remember, when we talk about standard enthalpy changes, right? Standard enthalpy change is the enthalpy change when molar amounts of reactants, as shown in the stoichiometric equation, react to form products. So, as shown in the equation, we have a total of 4 moles of reactants, and we have a total of 7 moles of products, right? So, A is incorrect because we're not showing 1 mole of products here. It's not when a total of 1 mole of reactants is reacted either, because again, we have 4 moles reacting, not 1, okay? When 1 mole of water reacts, again, that's not the answer because we have 3 moles of water shown. The enthalpy change when 6 moles of hydrogen fluoride are produced, yes, that is the answer, because again, when we talk about enthalpy changes or standard enthalpy changes, the coefficients in the equation represent the actual quantities in moles, not just ratios. So in this case, we're showing 6 moles of hydrogen fluoride being produced, so the answer is D. Molten aluminum chloride has a simple molecular structure. Each molecule consists of 2 aluminum atoms and 6 chlorine atoms. Which statement is correct? All the chlorine atoms in 1 gram of molten aluminum chloride have the same mass. This is not correct, okay? The relative atomic mass of chlorine is 35.5. However, when we talk about individual atoms, there could be chlorine 35 isotopes or chlorine 37, right? We talk about individual atoms, it could be either one of these two isotopes, right? This is just the average mass, the weighted average mass of the isotopes. So not all the chlorine atoms will have the same mass, right? These are the two main isotopes of chlorine that we've learned about. 1 mole of molten aluminum chloride contains 6.02 into 10 to the power 23 aluminum atoms. That's not true either because each molecule contains 2 aluminum atoms and 6 chlorine atoms, right? This is Al2Cl6. So 1 mole of molten aluminum chloride, 1 mole of this guy, 1 mole of this guy will contain 2 moles of aluminum atoms, which is 2 times 6.02 into 10 to the power 23. So it's not B, right? It's not B. 1 mole of molten aluminum chloride contains 3.61 into 10 to the power 24 chlorine atoms. Now 1 mole of Al2Cl6 has 6 moles of chlorine atoms. It has 6 moles of chlorine atoms, which is basically 6 times 6.02 into 10 to the power 23, and that gives us 3.61 into 10 to the power 24 chlorine atoms. So the answer is C. Which atom contains 4 times as many neutrons as the lithium-7 atom? So lithium-7 atom has atomic number 3, lithium, and the mass number is 7. The number of neutrons is just 7 minus 3, which is 4. So we have 4 neutrons. So which atom contains 4 times as many neutrons? That would be 16 neutrons. And the answer over here is C, right? Mass number 31, atomic number is 15. We have 31 protons and neutrons. We have 15 protons. So we have 31 minus 15 neutrons. Okay, so the answer is C. Which statement about the first ionization energies of magnesium and neon is correct? Now, first of all, when we talk about ionization energies, okay, they're always endothermic. Okay, ionization energies are always endothermic. That eliminates options B and D, right? Because both will be endothermic. And as far as the greater value is concerned, looking at the periodic table, we can see that neon is in period 2, right? The ionization energies increase across the period. They increase across the period. And then if we go to the next period, we've increased the number of shells. So there is a sharp decrease from neon to sodium. And then magnesium is slightly higher than sodium, okay, but it'll be much lower than neon. Okay, it'll be much lower than neon. To give you guys an idea of what that looks like, right? What we have is increase in ionization energy across the period. Okay, neon will be somewhere here, and then you're going to see a sharp decrease to sodium. Okay, and then you're going to see magnesium somewhere over here. Okay, so magnesium will be much lower than neon. Okay, will be somewhere over here. So neon has the greater numerical value. In a sample of pure water, what is the maximum number of hydrogen bonds that one molecule of water can be involved in? Now, we think about a molecule of water, right? We have H2O. The oxygen has two lone pairs, right? So each of these hydrogen atoms can be involved in hydrogen bonds with neighboring water molecules, and then each of the lone pairs on the oxygens can also be involved in hydrogen bonds with the neighboring molecules. The maximum number of hydrogen bonds that one molecule of water can be involved in is 4. And that's exactly what we see in the structure of ice. Hydrated cobalt-2 sulfate loses water when heated to give anhydrous cobalt-2 sulfate. All the water of crystallization is lost to the atmosphere as steam. When 3.1 grams of hydrated cobalt-2 sulfate, that's COSO4.X H2O, is heated to constant mass, the loss in mass is 1.39 grams. What is the value of X to the nearest whole number? So over here, okay, what we're doing is we're taking these hydrated crystals of cobalt-2 sulfate, right, COSO4.X H2O, and when we heat them, right, we're left with anhydrous cobalt-2 sulfate, and the water over here is driven off, right? That's X H2O. We want to find the value of X. That's basically just the molar ratio between cobalt-2 sulfate and water, right? We want to find that ratio, right? For every 1 mole of cobalt-2 sulfate, we get X moles of water. In order to find this molar ratio, we first have to find the moles of cobalt-2 sulfate and the moles of water, right? Now we know that the loss in mass is 1.39 grams. The loss in mass is 1.39 grams. In other words, 1.39 grams of water are driven off. 1.39 grams of water are driven off. And we had a total mass of 3.1 grams. So then how many grams do we have of the anhydrous cobalt-2 sulfate? That is 3.1 minus 1.39, which is 1.71 grams. 1.71 grams. So we can find the number of moles of the anhydrous cobalt-2 sulfate. Okay, cobalt from the periodic table we can see has a relative atomic mass of 58.9. Sulfur is 32.1, oxygen is 16. So we can say that over here the number of moles is 1.71. That's the mass divided by the MR, or the molar mass, which will be 58.9 plus 32.1 for sulfur, and then we have 4 oxygens, that's 64, and that gives us the number of moles of cobalt-2 sulfate as 0.011 moles. Okay, so we get 0.011 moles of cobalt-2 sulfate. As far as the moles of water are concerned, that's again the mass divided by the MR, 1.39 divided by 18. The number of moles of water is 0.072 moles. So then the ratio of the number of moles of cobalt to and water is 0.011 to 0.072. If we round this to the nearest whole number, we get the ratio 1:7. So that means that the value of X over here is 7. So the answer is C. The table shows bond energies for some diatomic molecules. Deuterium is an isotope of hydrogen. Okay, we're going to use the symbol D for deuterium. That's just hydrogen 2. Okay, this is just hydrogen 2. Which statements are correct? Diatomic molecules have exact values for their bond energies which are always positive. Statement 1 is true. Okay, we can determine the exact bond energies for diatomic molecules. Okay, and bond energies are always endothermic. Okay, they're always endothermic. The bond energy is just the energy required, which means that it's positive. It's the energy required or the energy needed to break 1 mole of covalent bonds in the gaseous state. The trend in group 7 bond energies can be explained by the variation in instantaneous dipole induced dipole forces. This is not true. Okay, this is not true. These are intermolecular forces, okay? These are intermolecular forces. Intermolecular forces explain the trend in boiling points, okay? They explain the trend in boiling points, volatility, etc., right? They predict the trend in physical properties, okay? They do not explain the trend in the bond energies. The bond energies can be explained by the atomic radius, right? The atomic radius is increasing down the group, so the bond energies are decreasing. Fluorine is actually an exception. Okay, fluorine is actually an exception to that trend. And statement 3 says the value for the enthalpy change for the reaction between deuterium and chlorine can be calculated using these data alone. That is not true, okay? If we had a reaction between deuterium and chlorine, again, think of deuterium as just an isotope of hydrogen, right? We'd get deuterium chloride, again, similar to HCl. Now we have the bond energies for deuterium and chlorine, but we would also need the bond energy for the DCl bond, which is not available to us. We do not have this bond energy, and therefore we cannot calculate the enthalpy change if we don't have the bond energy for the product. Okay, so statement 3 is also incorrect. So the answer here is A. Okay. Two procedures are described. Sulfur is burned in an excess of oxygen, and then nitrogen monoxide is added to the product mixture. Statement 2 says sulfur is burned in an excess of oxygen, and then nitrogen dioxide is added in the product mixture. Which procedures will produce some sulfur trioxide? Now we know that both oxides of nitrogen can catalyze the formation of sulfur trioxide from sulfur dioxide, okay? Both oxides of nitrogen can catalyze this. If nitrogen monoxide was a catalyst, okay, if nitrogen monoxide was a catalyst, it would first make nitrogen dioxide, and then the nitrogen dioxide can react with the sulfur dioxide to make sulfur trioxide, and we regenerate the nitrogen monoxide catalyst. Okay, we regenerate the catalyst. Now, if nitrogen dioxide was present, okay, if nitrogen dioxide was present, it would first react with the sulfur dioxide. And then the nitrogen monoxide that's produced can react with oxygen to reform the catalyst, which is nitrogen dioxide. So in the first case, we see nitrogen monoxide behaving as a catalyst, is regenerated at the end of the reaction, and in the second case, nitrogen dioxide is the catalyst and is regenerated at the end of the reaction. In both cases, we have the same overall equation. Sulfur dioxide is being converted to sulfur trioxide. Okay, so oxides of nitrogen, both nitrogen dioxide and nitrogen monoxide, can catalyze the formation of sulfur trioxide. So the answer here is A. In both 1 and 2, we're going to see sulfur trioxide being produced. Powder P is a mixture containing 2 of silver chloride, silver bromide, or silver iodide. Okay, so 2 of these 3 things are present. P is shaken with dilute aqueous ammonia. A yellow solid Q remains. The mixture is filtered and Q is washed and dried. The filtrate is collected and treated with aqueous nitric acid to produce a white precipitate R, which is filtered off, washed and dried. Q and R are warmed separately with concentrated sulfuric acid. Which observations are made? So over here, okay, we're starting with a powder P and we have dilute aqueous ammonia, right? So NH3 aqueous. And what we get is we get a yellow solid Q that remains, okay, when P is shaken with the dilute aqueous ammonia. So we can filter off that yellow solid, okay, and we get the filtrate, right? So here we get our yellow solid Q, and then here we have our filtrate, okay, Now this filtrate is treated with aqueous nitric acid to produce a white precipitate R. So what the aqueous nitric acid does is, it reacts with the ammonia present, right? And we're left with a white precipitate. Now, what could that white precipitate be? So again, over here, right, we had a mixture of 2 of these 3 compounds, okay? Now, the yellow solid that doesn't dissolve in dilute aqueous ammonia is actually silver iodide, right? Because silver iodide does not dissolve in dilute or concentrated ammonia, and we know that silver iodide is a yellow precipitate, right? So the yellow solid Q is silver iodide. And what does dissolve in the aqueous ammonia? Well, that has to be silver chloride. Okay, the silver chloride dissolves in the aqueous ammonia. It dissolves in the aqueous ammonia. But then when we react the nitric acid reacts with the ammonia. That means there is no longer ammonia present to dissolve the ammonia. The ammonia reacts with the nitric acid. Ammonia reacts with the nitric acid, which means that there is no more ammonia present to dissolve the silver chloride. So the white precipitate that we see at the end is the silver chloride that initially dissolved in the ammonia, but because the ammonia is neutralized by the nitric acid, we see that white precipitate again. Now, if we react Q with concentrated sulfuric acid, right, that's basically iodide reacting with concentrated sulfuric acid. Iodide is a very strong reducing agent. So the iodide ends up making iodine. So we're going to see violet fumes of iodine. And then R, which is our white precipitate at the end, is chloride, and chloride does not produce concentrated sulfuric acid. Remember, the reducing strength of the halides decreases down the group, right? So iodide is the strongest reducing agent. Iodide and bromide can both reduce concentrated sulfuric acid. With iodide, you see violet fumes. With bromide, you would see orange fumes, but we don't have bromide over here. With chloride, we just see an acid-base reaction, okay? So we're going to see HCl being produced. So we're going to see steamy or misty fumes of HCl, okay? So we're going to see iodine vapor with silver iodide, that's Q, and then R is silver chloride. We're going to see steamy fumes of HCl. So the answer over here is B. Two period 3 elements X and Y burn separately in oxygen to form solid oxides. The oxide of X is insoluble in water. The oxide of Y dissolves in water to form a solution which dissolves the oxide of X. What could X and Y be? So the oxide of X is insoluble in water. That's true for aluminum, magnesium, and silicon, right? All three oxides are insoluble in water. The oxide of Y dissolves in water to form a solution which dissolves the oxide of X. Right, now sodium forms sodium hydroxide, right? So when the oxide of Y dissolves in water, we get sodium hydroxide, we get NaOH, and we know that NaOH can dissolve aluminum oxide, right? Because aluminum oxide is amphoteric. You might remember this reaction. It's Al2O3 plus NaOH plus H2O gives us NaAlOH4. The balanced equation for this is Al2O3 plus 2NaOH plus 3H2O gives us 2NaAlOH4. So this guy over here, okay, is soluble in water. Okay, this salt that we get is soluble in water. So again, aluminum oxide is amphoteric, so it can react with acids and bases. So it reacts with sodium hydroxide. Okay, it dissolves in sodium hydroxide. It also dissolves in HCl. Okay, it doesn't dissolve in water, but it can dissolve in acid or alkali. So the answer is A. Okay. The oxide of aluminum oxide is insoluble in water, but it does dissolve in sodium hydroxide. Now, one thing I want to mention here is that silicon 4 oxide, okay, silicon 4 oxide or silicon dioxide also dissolves in sodium hydroxide, okay? But we didn't have the option here of sodium hydroxide. And both aluminum oxide and silicon oxide, okay, they both dissolve in hot concentrated sodium hydroxide. Okay, I'll just make a note of that here. Both silicon 4 oxide and aluminum oxide, okay, dissolve in hot concentrated sodium hydroxide. Okay, they both can dissolve in hot concentrated sodium hydroxide. Aluminum oxide is amphoteric, so it can react with bases, and silicon 4 oxide is acidic, so it can react with alkali as well, as long as it's hot and concentrated. Which row describes the structure and bonding of silicon 4 oxide and silicon tetrachloride or silicon 4 chloride? Now, silicon 4 oxide has a giant covalent structure or a macromolecular structure similar to that of diamonds, right? Each silicon atom is tetrahedrally bonded to 4 oxygens, and each oxygen is bonded to 2 silicons in that structure. Okay, I'll also draw the structure over here, or part of the structure. Okay, this is what the structure of silicon 4 oxide looks like. And we have a macromolecule. We have a macromolecule where each oxygen is bonded to 2 silicons, and each silicon is tetrahedrally bonded to 4 oxygens. Okay, we have a macromolecular or giant covalent structure for silicon 4 oxide, and then silicon tetrachloride or silicon 4 chloride is actually a liquid at room temperature because it has a simple covalent structure. Okay, it has a simple covalent structure. So the answer is B. A sample containing 0.010 moles of anhydrous calcium nitrate is heated strongly until it fully decomposes. All the gas produced is collected and its volume measured at room conditions. What is the volume of gas produced? So first let's write down the equation for the decomposition of calcium nitrate. That's CaNO3 twice. Right, it decomposes to form calcium oxide, nitrogen dioxide, and oxygen gas. And 1 mole of calcium nitrate will give us 1 mole of calcium oxide, 2 moles of nitrogen dioxide, and half a mole of oxygen. So what we can see over here is that 1 mole of the nitrate, okay, 1 mole of the nitrate gives us 2.5 moles of gas. 1 mole of the nitrate gives us 2.5 moles of gas. So if I have 0.010 moles of the nitrate, that's what they've told us in the question, right, I'm going to get 2.5 times the number of moles of gas. So in this case, I would get 0.025 moles of gas. We want to find the volume of gas produced at room conditions, right? The volume of gas at room conditions. We have the number of moles of gas. We know that the volume occupied by the gas is just the number of moles times 24,000, right? Where 24,000 centimeter cube is the molar volume of a gas in cm cube. So this will be 0.025 times 24,000, which gives us the volume of gas as 600 centimeter cube. Okay, so that's the volume of gas that's being produced. V and Z are both elements in period 3 of the periodic table. Each element forms one stable ion that does not contain another element. The atomic radius of each element and the ionic radius of the ion described above is shown. Which statement is correct? So in the case of V, the ionic radius is smaller than the atomic radius. Is V a cation or an anion? V must be a cation, right? Because in cations we have fewer electrons, right? Usually we have fewer shells, which means that the ionic radius is smaller than the atomic radius, okay? So V is a cation, in other words, a positively charged ion. In the case of Z, the ionic radius is greater than the atomic radius, which means that the ion of Z must be an anion, right? The ion of Z must be an anion, so it's a negatively charged ion. So ions of V and Z have the same number of full electron shells. Ions of V and Z have the same number of full electron shells. Well, both V and Z are in period 3 of the periodic table. So when we talk about the atoms, right, there's a total of 3 shells for both atoms. Period 3 means there's a total of 3 shells. When we talk about the cation, the valence electrons have been lost to form the cation, which means that the ion has 2 shells, whereas in the anion, we're still going to have 3 shells. So they do not have the same number of shells. Okay. Ions of Z are positively charged. That's incorrect. We just established that they're negatively charged. Z has a greater electronegativity than V. The third statement is correct because as we go across the periodic table, we go from forming cations to forming anions, right? And the electronegativity also increases across the period. The electronegativity increases across the period. The reason why is because the nuclear charge increases, the number of shells remains the same. The tendency to attract electrons increases. In group 2 of the periodic table, the properties of the elements and their compounds show a regular change down the group. Which property shows a decrease from magnesium to barium? The decomposition temperature of the carbonates and the decomposition temperature of the nitrates increases down the group, okay, because the thermal stability increases. So A and B are incorrect. The solubility of the hydroxides also increases down the group, whereas the solubility of the sulfates decreases down the group. So the answer is D. 4 properties of beryllium or a beryllium compound are listed. Which property is different from the property of magnesium or the equivalent magnesium compound? B reacts with O2 when heated in air. So beryllium reacts with oxygen when heated in air. Magnesium does not. That's incorrect. Okay, they both react. They both react with oxygen to form the oxide. Okay, with beryllium you'll get beryllium oxide. With magnesium you'll get magnesium oxide. B reacts with aqueous sulfuric acid to form metal sulfate and hydrogen gas. Magnesium does not. Again, that's not true. They're both reactive metals. They both form salt and hydrogen gas when reacted with acid. Barium nitrate decomposes on heating to form a metal oxide, nitrogen dioxide, and oxygen. Magnesium nitrate does not. Again, this is incorrect. They both decompose to form the oxide, nitrogen dioxide, and oxygen. That leaves us with D. Okay. Beryllium chloride reacts with water to form fumes of HCl. Magnesium chloride does not. This is true because beryllium chloride is a covalent compound. Okay, it's a covalent compound, so it's hydrolyzed by water. Okay, it's hydrolyzed by water and hence it forms an acidic solution, similar to what happens with aluminum chloride. Whereas magnesium chloride, okay, it's mostly ionic in nature. It does form an acidic solution, but a very slightly acidic solution, and you do not see white fumes of HCl. Which two formulae correctly represent a pair of structural isomers? Now, if two things are structural isomers, first of all, they have to have the same molecular formula, right? Because they're isomers, they have to have the same molecular formula, but different structural formulae, right? Different structural formula or different structures. Now, if you look at option A, both the options are the same, okay? Both the options are the exact same, right? You have a CH3 bonded to a CH, bonded to a CH3, right? And then that's bonded to a CO2H, right? So here they just group the two CH3s together, whereas here they've shown them separately, but in both cases you have the two CH3s bonded to a CH, okay? So A, they're not structural isomer, they're the same compound. In B, again, they're the same, right? You have a CH bonded to two CH3s and a COOH, CH bonded to COOH and two CH3s, and same thing here, CH bonded to two CH3s and COOH, so they're the same thing. In C, they actually have different molecular formula. You have a 3-carbon compound versus a 4-carbon compound. That means that they are not structural isomers at all. And then D, these are structural isomers. Here you have a 4-carbon chain, and here you have a 4-carbon compound, which you have a branched chain, right? You have a 3-carbon chain. So this guy over here is this, right? This is 2-methyl propanoic acid, and this is butanoic acid. So the answer is D. Okay. Which reagents and conditions would result in the formation of butane nitrile? 1-bromobutane is heated under pressure with ammonia and ethanol. That's not true. Okay, this results in the formation of an amine, not a nitrile. 1-bromopropane heated with potassium cyanide in ethanol. Okay, so if you have 1-bromopropane, okay, 1-bromopropane is CH3, CH2, CH2, Br, right? So 3-carbon halogenoalkane. And if we heat this guy with KCN and ethanol, we heat this guy with KCN and ethanol and we heat, right, what we get is a nucleophilic substitution reaction where we get CH3, CH2, CH2, and then we get a CN, right? The cyanide substitutes for the bromine. So we get a 4-carbon nitrile, which is butane nitrile. So the answer here is B. Compound X, C7H13Br, reacts with hot alcoholic sodium hydroxide to produce two compounds Y and Z. On reaction with bromine, Y gives a product C7H12Br2, which exists as a mixture of 4 optical isomers. On reaction with bromine, Z gives a product C7H12Br2, which is non-chiral. What could X be? So the first reaction here, when we react compound X with hot alcoholic sodium hydroxide, that's sodium hydroxide and ethanol, we get an elimination reaction. Okay, and elimination ends up making alkenes. Okay, so this is elimination of halogenoalkane to make alkenes. So Y and Z are alkenes. Okay, they have a carbon-carbon double bond. So the first question is, which of these compounds results in a mixture of two different alkenes, Y and Z? Now when we talk about elimination, what we get is a halogen being removed and a hydrogen from the neighboring carbon being removed. Okay, so the halogen is on this carbon, right? The halogen is on this carbon, and the neighboring carbon's hydrogen will be removed. Now we can remove this hydrogen or this hydrogen, they're the same thing, or we can remove a hydrogen from here. So we would get two different things here, right? We can either get this guy, right, where we have a CH3 and the bromine is removed, and either this hydrogen or this hydrogen is removed. Either one doesn't make a difference, right? It's the same thing. So we get a double bond here, or we can get this guy over here, right, a CH2. Again, the bromine is removed from this carbon and the neighboring carbon's hydrogen is removed. So we will get two different compounds here. Okay, in the case of B, if we're going to remove the bromine and we're going to remove a neighboring hydrogen, we only have one option, right? So the bromine will be removed and this hydrogen will be removed, and we get a double bond here. So we only get one product, right? We don't get two different products. So it can't be B, right? Because we have to get two different compounds from elimination. In the case of C, again, the halogen is removed from this carbon, and then a hydrogen from the neighboring carbon is removed. So we can have a hydrogen being removed from here or a hydrogen being removed from here, right? So what we would get then is, we would get this guy with a CH3, the bromine is removed. If the hydrogen is removed from this carbon here, we get a double bond here. And if the hydrogen is removed from this carbon, then we would get a double bond there, right? So we'd get a double bond here. So again, we're getting two different structural isomers here. And then in the last case, right, bromine removed from here, and then hydrogen can be removed from here or here, right? So what we would get then is, we would get this guy, and then we would either get a double bond over here, right, if this hydrogen is removed, or if it was removed from here, we get a double bond over here. So these are our two possible structural isomers. Now in reaction with bromine, one of these compounds gives a product which exists as a mixture of four optical isomers. Okay, so let's start with this compound here, right? If we take this compound, here, we reacted with bromine, we're gonna have an electrophilic addition reaction, right? And we're gonna see the addition of bromines across the double bond, right? So we're gonna see two bromines being added. Now this guy has two chiral centers, which means we have a total of how many optical isomers? We have a total of 4 optical isomers, right? 2 squared. So we can have this carbon which has either arrangement, the clockwise or the counterclockwise, and this carbon that can have counterclockwise or clockwise arrangements, right? So 2 possibilities here, 2 possibilities here. So that's 2 times 2. Again, notice how these chiral centers are asymmetric, right? So each of these carbon atoms is bonded to 4 different atoms or groups of atoms. So yes, this must be Y. This must be Y. It's giving us 4 different optical isomers. And in the case of Z, we're saying that if we add bromine to this compound, we get a product which is non-chiral. Okay, so over here again, bromine will be added across the double bond, right? So we're going to get a bromine on this carbon. This will become CH2Br, and we're going to get a bromine on this carbon over here. Okay, and notice how this molecule is non-chiral. This carbon atom is not a chiral center, okay, because there is a line of symmetry through this carbon. Okay, so this is not an asymmetric carbon atom. This group either side of this line is the same. Okay, so this is not a chiral center. Chiral centers have to be asymmetric. So the answer is A. Y gives a mixture of 4 optical isomers. Right, that's 2 squared. That's 4 optical isomers. And Z gives a product which is non-chiral. When illudine S is heated under reflux with an excess of acidified potassium dichromate 6 compound M is formed. What is the molecular formula of compound M? Now dichromate 6 is an oxidizing agent. It's a relatively mild oxidizing agent that can oxidize aldehydes, okay, or primary and secondary alcohols, right? The primary and secondary alcohols will react with dichromate 6. Now over here, this OH, right, this is a tertiary alcohol. This carbon that's bonded to the OH is bonded to 3 carbon atoms, so this guy won't react. This guy over here is a primary alcohol, it's a CH2OH, so this will become a CO2H, right? And this guy over here is a secondary alcohol, so it will become a ketone, right? This is a CHOH, so this will become a ketone, so it will become a CO. So if you had to draw the structure of the product here, what we would get is this guy will become a C double bond O, right? And this guy will become a CO2H. Okay, nothing will happen to the ketone, nothing will happen to the alkene, so none of the other groups will react. Then what's the molecular formula for this compound? So this compound obviously has 15 carbons because all the options have 15 carbons. As far as the number of oxygens is concerned, we have 1, 2, 3, 4, and then 5 oxygens. So it has to be B or D. It can't be A or B, right? Because there's not 4 oxygens here. So we've narrowed down our choices. Now we just have to count the number of hydrogens. Okay. So we can just count the total number of hydrogens here. Okay, we have 2 here, we have 2 here. So that's 4. We have none over here, we have none over here, we have none over here. We have 1 here, so that's 5. We have none here, we have none here. We have none over here, we have none over here again. All of these carbons are shown with 4 bonds. We have a CH3 here, so we have 3 over here. We have a CH3 over here, so we have 3 over here. We have a CH3 over here, so we have 3 over here. This carbon is shown with 3 bonds, so we have 1 here, right? So that's 1 over here, and then we have 1 over here, which gives us a total of 1 plus 3, 4, 4 plus 4, 8, plus 3, 11, 11 plus 1, 12, 12 plus 3, 15, 15 plus 1, 16. So we have 16 hydrogens, which means that the answer is B. I have taught you guys a simpler method, okay? I have taught you guys a simpler method for calculating the number of hydrogens, okay? This only applies to compounds that contain carbon, hydrogen, and oxygen, okay? For compounds containing carbon, hydrogen, and oxygen, we can start with the number of carbon atoms, okay? And let's treat it as an alkane. If it was an alkane, there would be 32 hydrogens, right? There would be 32 hydrogens, and then you're going to subtract 2 hydrogens for every double bond and every ring. Okay, for every pi bond and every ring, you're going to have 2 fewer hydrogens because each carbon can then bond to 2 fewer hydrogens. So over here, we have 1 pi bond here, 1 pi bond here, 1 pi bond here, that's 3, 4, and then 5. So we have 5 pi bonds. So we're going to subtract 2 hydrogens for every pi bond, and then we have 1, 2, 3 rings over here. We're going to subtract 2 hydrogens for every ring, and that leaves us with 16 hydrogens. So that is a method that you can use as a short form for calculating the number of hydrogen atoms. Cyclohexene C6H10 is a hydrocarbon with a 6-membered ring of carbon atoms. It has several structural isomers that are straight chain alkenes. The number of double bonds in each of these molecules is P. What is the shape of the cyclohexene molecule and what is the value of P? So cyclohexene is C6H10, right? There's 1 double bond there. So first of all, is this molecule planar or non-planar? So in this compound, each of these carbon atoms have tetrahedral geometry. Okay, each of these carbon atoms have tetrahedral geometry because they're bonded to 4 different atoms or groups of atoms, which makes this compound non-planar. And if we were talking about straight chain alkenes, how many double bonds would a straight chain alkene have for it to have the same molecular formula? So if you had a straight chain alkene, right, that means you have 6 carbon atoms in a straight chain like this. If you just had 1 double bond, that would be C6H12. So that straight chain alkene would have to have 2 double bonds. So an example of this is An example of this is this guy, which is hexa 1,5-diene. Okay, if you notice, this guy has a total of 10 hydrogen atoms, right? 2 plus 1 3, 3 plus 2 is 5, plus 2 is 7, and plus 1 plus 2 is 10. Okay, so this is C6H10. So the number of double bonds in each of these straight chain alkenes would have to be 2 for it to have the molecular formula C6H10. So the answer is D. Exhaust gases from an internal combustion engine are made less harmful by passing them through a catalytic converter. A number of reactions take place in the catalytic converter. 2 such reactions are described in the table. Which row is correct? In a catalytic converter, carbon monoxide is removed by a reaction with nitrogen monoxide. Okay, it reacts with nitrogen monoxide to form carbon dioxide and nitrogen gas. Okay, the reaction that we have is this guy over here. Okay, this is the reaction that takes place in a catalytic converter, and this helps us get rid of carbon monoxide and nitrogen monoxide. Now, carbon monoxide is being oxidized to carbon dioxide. So when we talk about carbon monoxide specifically, okay, it's oxidation because carbon monoxide is being oxidized. And then unburned hydrocarbons, okay, I'm just going to use CXHY for unburned hydrocarbons, react with oxygen to form carbon dioxide and water. Okay, in a catalytic converter, again, this is an oxidation reaction, right? Combustion is an oxidation reaction. So the unburned hydrocarbons are being oxidized. So the answer over here is A. In this case, the catalyst being used is platinum or rhodium. Okay, those are the most common choices. We can use platinum, rhodium, palladium. These are inert metals. Okay, relatively expensive, but we use a very small amount. Which compound reacts most rapidly with aqueous silver nitrate by an Sn1 mechanism? So over here we have 1 chloromethylpropane, 2 chloromethylpropane, 1 iodomethylpropane, and 2 iodomethylpropane. So in each of these cases, we have methylpropane, which is this guy, right? We have a 3-carbon chain with a methyl group. Methyl group has to be on the middle carbon. Okay, so it will be carbon number 2. And then we have a halogen bonded, right? Now, if you're talking about 2-chloromethyl or 2-iodomethylpropane, these are tertiary halogenoalkanes. Okay, these are tertiary halogenoalkanes. And tertiary halogenoalkanes react via an Sn1 mechanism, right? Sn1 mechanism is favored by tertiary halogenoalkanes, right? In which we form a carbocation intermediate, so we get a tertiary carbocation intermediate. So if the Sn1 mechanism is taking place, we know that it has to be a tertiary halogenoalkane, so it can't be A or C, right? The carbon with the halogen has to be bonded to 3 carbon atoms. The carbon with the halogen has to be bonded to 3 carbon atoms for it to undergo an Sn1 mechanism. Okay, in the cases of A and C, the halogen will be on carbon number 1, so it will be one of these carbons here. Okay, it can't be A or C. Now, iodoalkanes will react faster than chloroalkanes. Okay, the rate of reaction will be faster for iodomethylpropane than it would be for 2-chloromethylpropane. The reason why the rate of reaction is faster is because the bond energy of the carbon iodine bond, okay, is lower. In other words, a weaker bond than the carbon chlorine bond. So that means lower activation energy and therefore a faster rate of reaction for the iodomethylpropane or 2-iodomethylpropane. Tartaric acid, given the structure here, is found in many plants. A sample of tartaric acid reacts with excess of lithium aluminum hydride to form the organic product J. What happens when aqueous sodium hydroxide is added to separate samples of tartaric acid and J? Now, lithium aluminum hydride is a reducing agent. Okay, so it will reduce the carboxyl group. Okay, it will reduce the carboxyl group or the carboxylic acid to primary alcohols. So the product J over here, okay, the COOH will become a CH2OH. So what we get is we get this guy. Okay, we get CH2OH. This guy will become a CH2OH. Then we have CHOH, and then a CH2OH. Okay, so this is the product J. Now, as far as the reaction with sodium hydroxide is concerned, sodium hydroxide will react with a carboxylic acid, right, in a neutralization reaction. It can react with the carboxylic acid because it's a base. It can react with acids, whereas J will not react with sodium hydroxide. Okay, it will not react with sodium hydroxide because it does not have an acid group anymore. So only tartaric acid will react. Citric acid can be converted into tricarboxylic acid in 2 stages. An intermediate Q is formed. Which reagents are needed for each stage? So in the first stage, we're forming compound Q, that's our intermediate compound. In the second stage, we're converting citric acid to tricarboxylic acid. Now the first thing you notice is that in stage 1, we're probably removing this OH group because this OH group is not present in the final product. So which of these reagents would help us remove this OH group? In order to remove this OH group, okay, stage 1 must be a dehydration reaction. Okay, must be a dehydration reaction, which is just elimination of H2O, right? What happens here is that the OH group is removed and a hydrogen from a neighboring carbon is removed. So it could be this hydrogen or this one. They're the same thing, right? Because there's a symmetry here. So it could be this hydrogen or this hydrogen. So in stage 1, we would get compound Q, which is this guy, right? The OH is removed, and let's say that this neighboring hydrogen is removed. So we will get a double bond here. This will become a CH and then a COOH, and then this guy over here will remain a CH2, COOH, and then obviously we have a COOH over here. And then in the second stage, we can react Q with hydrogen and nickel. That's hydrogenation. It's hydrogenation, and then we're just going to end up adding the 2 hydrogens back. Okay, so hydrogen and nickel, and we heat. This is hydrogenation or reduction, and we end up adding a hydrogen here, so that becomes a CH, and this CH over here becomes a CH2. So for dehydration, we can use concentrated sulfuric acid, or we can use aluminum oxide as our catalyst, and we heat. Okay, so these are the reagents we need for dehydration: concentrated sulfuric acid. In stage 2, it's hydrogenation, so we're using hydrogen and nickel. So the answer is A. Structural and stereoisomerism should be considered when answering this question. P has molecular formula C5H10O. P produces an orange precipitate with 2,4-DNPH. How many isomeric structures does P have? Let's actually solve this separately. Okay, I'm going to take this question here, solve it on a blank canvas. And what we have here is we have a compound that has molecular formula C5H10O, and because it reacts with 2,4-DNPH, right? Because it reacts with 2,4-DNPH, this is a test for carbonyl compounds. Okay, this is a test for carbonyl compounds. So that means that P must be an aldehyde or a ketone, right? It must be an aldehyde or a ketone. So we have to figure out how many possible structures we have. So we're going to start with aldehydes. Okay, we're going to start with aldehydes here, because we can have aldehydes or ketones. And now for aldehydes, we have a specific functional group. We can look at chain or position isomerism. Now for aldehydes, the position will always be carbon number 1, right? Because we have a CHO group that will always be at the end. So it will always be carbon 1, so we can only have chain isomers. So we're going to start with a 5-carbon chain, right? That will be the simplest guy over here. So that will just be CH3, CH2, 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 and then CHO, right? That's pentanal. Now we can have a 4-carbon chain, right? That would be a branched chain. In that case, we're going to have this again. We have a CHO group on carbon number 1, and then the branch can go on this carbon or on this carbon. You can have a branch here. That would be a CH3. So then we have CH3, CH2, and then a CH bonded to a CH3, and then a CHO. Or we can have the branch on carbon number 3, right over here. So then that would be 2 CH3s bonded to a CH and then a CH2 CHO. This is 2-methyl butanal and this is 3-methyl butanal. 2-methyl butanal, 3-methyl butanal. Lastly, we can have a 3-carbon chain, right? If we add a 3-carbon chain over here, then what do we have? For a 3-carbon chain, we would have something like this. Right? We have carbon, carbon, carbon like this, CHO, and then we have a CH3 here, we have a CH3 here, and we have a CH3 here. Right? That's the only possibility with a 3-carbon chain. So there's 4 structural isomers that can be aldehydes with the molecular formula C5H10O, right? 5 carbon aldehydes. We also have to consider stereoisomerism. Do any of these compounds show stereoisomerism? We talk about stereoisomerism, we're talking about geometric or optical isomerism. There's no geometric here because there's no double bonds, but there is optical isomerism, right? If you look here, this guy over here has no chiral centers. You look at the 4 carbon chain compound, you see that 2-methylbutanal has a chiral center, right? This carbon atom is bonded to 4 different atoms or groups of atoms. So this guy could be one of 2 different optical isomers. So this structure actually exists as 2 different optical isomers. So then we have one isomer here, that's pentanal. Then we have 2 different isomers of 2-methylbutanal. There's no chiral center here because this carbon is bonded to 2CH3, then there's no chiral center here either. So the total of 5 aldehydes, that have the molecular formula C5H10O, right? One of these structures, we have 4 structural isomers, and one of these structures actually exists as a mixture of, or can exist as a mixture of, optical isomers. Now we're going to look at ketones. So again, for ketones, we can start with a 5 carbon chain. Now for a 5 carbon chain, right, we can have propan 2-on, or we can have propan 3-on. We can have propan 2-on or propan 3-on. Remember, the ketone has to be on one of the middle carbons because there has to be carbon atoms either side of the C double bond O. Okay, so it could either be propan 2-on, which is the first guy that I've shown, CH2 and then CH3. Okay, or it has to be propan 3-on, which is just CH3, CH2, CO, CH2, CH3. Then if we talk about a 4 carbon chain, right, we're going to have a branched chain. The branching, whether we draw it on this carbon or on this carbon, it doesn't matter, it's the same thing. And then obviously the C double bond O has to go here, right, because none of the other carbons will make a double bond that will give you a ketone. So then we have a CH3 here, we have a CH3 here, we have an H, and then we have a CH3 here, right? And we can't have a 3 carbon chain. Okay, we can't have a 3 carbon chain because if we have a 3 carbon chain, there's no place that the ketone can go. The C double bond O can only go on the ends, which would then make it an aldehyde. Okay, so these are the only possibilities that we have for ketones. So these are the 3 structural isomers that we have for ketones. Do any of these exhibit stereoisomerism? None of these guys exhibit stereoisomerism. Again, there's no geometric because there's no double bond, and none of these structural isomers have a chiral center. So we just have 3 structural isomers that are ketones, okay, or 3 isomers that are ketones with the molecular formula C5H10O. So we have a total of 5 aldehydes and 3 ketones, which gives us a total of 8 isomers that are carbonyl compounds with the molecular formula C5H10O. All right, moving on. So the answer for question number 34 was D. 2 isomeric alcohols W and X have molecular formula C4H9OH. Okay, molecular formula C4H9OH. W is oxidized to carbonyl compound Y, which gives a red precipitate with Fehling solution. Carbonyl compound Y gives a red precipitate with Fehling solution. So what type of a carbonyl compound is Y? Now Fehling solution is a test for the CHO group. Fehling solution is a test for the CHO group, which means that compound Y must be an aldehyde. Compound Y must be an aldehyde because it's a carbonyl compound that has a CHO group, which means that the alcohol W must be a primary alcohol. Okay, this must be a primary alcohol. Okay, because primary alcohols are oxidized to aldehydes, right? So this is the primary alcohol, and then X is oxidized to carbonyl compound Z, which does not give a red precipitate with Fehling solution. That means compound Z is a ketone, right? Again, Z is a carbonyl compound, it's not an aldehyde because it doesn't give a red precipitate with Fehling, so it means it's ketone. And then that means that alcohol X must be a secondary alcohol. Okay. Secondary alcohols are alcohols in which a secondary alcohol is an alcohol in which the carbon with the OH is bonded to just one hydrogen and two carbons. So it has a CHOH group. Okay. Primary alcohol, the carbon is bonded to two hydrogens. Okay, the carbon with the OH and just one other carbon. Which of W and X gives the yellow precipitate with alkaline aqueous iodine? Now, alkaline aqueous iodine is a test for either the CH3CO group or the CH3CHOH group. Right? CH3CO group in carbonyl compounds or the CH3CHOH group in alcohols. Right? Now we know that W and X are alcohols. W and X are alcohols. So again, we're looking at this group here. We're looking at this group over here, right? And this group CH3CHOH, this group, the only primary alcohol that contains this group, is ethanol. Right? If we have a hydrogen here, that's the only primary alcohol that has a CH3CHOH group. Otherwise, this guy over here will be some carbon chain. Okay, this guy over here will be some carbon chain, so it won't be a hydrogen, right? It'll be an R group over here, and so therefore it will be a secondary alcohol. Again, the only primary alcohol is ethanol. That would give us a positive test with alkaline aqueous iodine. We know that the primary alcohol W is not ethanol because it's a 4-carbon alcohol. It's not a 2-carbon alcohol, so it's not ethanol. So we know that it's not W, which means that only X could potentially give us a yellow precipitate with alkaline aqueous iodine. Okay, this R group must be some carbon containing group for it to be a 4-carbon compound. So that means only X gives us a positive test with alkaline aqueous iodine. The ester ethyl butanoate can be hydrolyzed using an excess of dilute sodium hydroxide solution. Which substance is a product of this reaction? When we talk about ethyl butanoate, right, we have CH3CH2, that's ethyl, right, and this is the alcohol part, so ethyl, and then this guy is bonded to an oxygen, then we have C double bond O, and then we have butanoate, so we have a total of 4 carbons on the right of that oxygen, right? So this is ethyl, and then so this ester can be made using a 2-carbon alcohol and then a 4-carbon acid. Now when we hydrolyze this using aqueous sodium hydroxide, right, and heat, this is alkaline hydrolysis, right? We're going to break this ester linkage. That's going to be the bond between the C double bond O and the oxygen, the single bond, right? And what we're going to get is we're going to get ethanol, that's CH3CH2OH, and we're going to get the salt of the carboxylic acid. So we're going to get butanoate, sodium butanoate. We're going to get CH3, CH2, CH2, CO2 minus, and then Na plus, right? That's the salt of the carboxylic acid. So the answer over here is A. Right? We're going to get sodium butanoate and ethanol. So sodium butanoate is one of the products. An aqueous solution contains 4 grams of a carboxylic acid Q. When this solution reacts with an excess of magnesium, 380 centimeter cube of gas is produced, measured at STP. What is the relative formula mass of Q? Now STP, okay, STP is standard temperature and pressure, okay, and the table of constants and values given to you in the exam, okay, standard temperature and pressure is mentioned as 0 degrees Celsius and 1 atmosphere. Okay, this is different from standard conditions. Okay, and the molar volume of a gas is 22.4 decimeter cube, okay, per mole. This is the volume of a gas at STP. Again, standard temperature and pressure is different from standard conditions. Standard conditions is RTP, room temperature and pressure. Okay, that's 25 degrees Celsius. STP is different from standard conditions. Okay, that's 0 degrees Celsius in 1 atmosphere. So this is the molar volume of a gas. Okay, at standard temperature and pressure. Now, the first question I have is, before we do any calculations, what gas is being produced when magnesium, which is a reactive metal, reacts with carboxylic acid Q? The gas being produced is hydrogen gas. Okay, the gas being produced is hydrogen gas. So the first thing we can do is we can find the number of moles of hydrogen gas, right? The number of moles is the volume, that's 380 cm cube, divided by the molar volume. In this case, we're not going to use 24,000 cm cube, we're going to use 22,400 cm cube. So how many moles do we have of hydrogen gas? 0.017 moles of hydrogen gas. So we have 0.017 moles of hydrogen gas. Okay. Now let's assume that our carboxylic acid just has one carboxyl group, right? If I had 1 mole of carboxylic acid, how many moles of hydrogen gas would we get? 1 mole of carboxylic acid would mean we have 1 mole of these hydrogen atoms, right? We have 1 mole of these hydrogen atoms, which means that we would get half a mole of hydrogen gas. We would get half a mole of hydrogen gas, right? That's just 1 mole of hydrogen atoms. So if we're getting 0.017 moles of hydrogen gas, we're getting 0.017 moles of hydrogen gas. We have double the number of moles of the carboxylic acid. Again, for every half a mole of this, we have 1 mole of acid. We have twice the number of moles of acid. That would be 0.017 times 2, which is 0.034 moles. Okay? So we have 0.034 moles of the carboxylic acid. Now we know that the mass of the acid is 4 grams. The number of moles is 0.034 moles, which means we can find the molar mass, right? We know that the number of moles is the mass divided by the molar mass, right? Which means that the molar mass is just the mass divided by the number of moles, and this is equal to 4 divided by 0.034, which gives us the molar mass as, or the MR as, 117.65. So if we round that to the nearest whole number, we get 118, which means that the answer is B. That is a relative formula mass of Q. Question number 38 says the infrared spectrum of an organic compound is shown. Okay, they've given us the table with the absorptions for different bonds, okay, over here. Which compound could give this spectrum? Now, if you notice over here, compounds A, B, and D have an OH group, right? We have a CO2H here, that's COOH. So we have an OH group here, we have an OH group in B, and we have an OH group in D. If you look at the spectrum, is there an OH absorption present? The OH peak can come from a carboxyl group, from a carboxylic acid around 2500 to 3000, or it can come from an alcohol, right? A hydroxy group around 3200 to 3650, right? So for the OH, you would see a peak somewhere in this region. You'd see either this peak for an OH from an alcohol, right, a hydroxy group, or you'd see a very broad peak, because of a carboxylic acid. Do we see either of these peaks here? Do we see a very broad peak due to the OH from a carboxylic acid or an alcohol? The answer is no, right? There is no OH group present. We do see a peak around 1700, which means that a C double bond O group is present, right? A C double bond O group is present. So we have a compound that has a C double bond O. But does not have an OH bond, which means that the answer has to be C. Okay, compound C has a C double bond O, but it does not have an OH group. Cyclohexa 1,4-diene is treated with a solution of bromine in tetrachloromethane in the dark. Okay, tetrachloromethane is just a solvent. Okay? This is just an organic solvent. So we're simply reacting this guy with bromine. Which product is formed? This is just an electrophilic addition reaction, right? This is addition of bromine to an alkene. So what will happen is that the bromine will simply add on across the double bonds, right? So we'll get 2 bromines being added here across this double bond, and then 2 bromines will add across this double bond. So this will be the product. Okay, so the product over here is B. Okay, we'll have 2 bromines added across each of the double bonds. So the answer is B. 2-methyl-butene is reacted with hot concentrated acidified potassium manganate 7 solution. What are the products of this reaction? So let's first draw out the structure of 2-methyl-butene. We have butene, which is, we have a 4 carbon chain, that's but, and we have a double bond on carbon number 2, and then we have a methyl group on carbon number 2 as well. Okay, so this is 2-methyl-butene, right? This is carbon number 2. Now when this guy reacts with hot concentrated acidified manganate, right, this is strong oxidation of alkenes. This is strong oxidation of alkenes. So we rupture this double bond. Now what happens to this carbon atom here? Now when we talk about strong oxidation of alkenes, when we talk about the carbon on the double bond, if that carbon atom is bonded to two carbon atoms, it becomes a ketone. Okay, it becomes a ketone. I'm going to call this compound A, let's say, right, the product that is formed as a result of this carbon being oxidized, right? This carbon here, this carbon over here becomes a C double bond O, and nothing happens to the alkyl groups, okay? So it will still be bonded to two CH3s. So one of the products will be propanone. Okay, one of the products will be propanone, which only leaves us with options A or B. Again, if the carbon on the double bond is bonded to two carbons, that carbon will become a ketone. Okay, that carbon will become a C double bond O. Nothing will happen to the CH3s. Now, if on the double bond we have a carbon that's bonded to one hydrogen and one carbon. Again, if you look at this carbon, it's bonded to one hydrogen. This carbon will become a CO2H group. Okay, I'm going to call this product B. Okay, this carbon over here, this carbon is bonded to just one hydrogen. This carbon will become a CO2H or a COOH group. Okay, and then nothing will happen to the alkyl group. So the other product that we get is CH3CO2H, which is ethanoic acid. So if we have a carbon on a double bond that's bonded to just two other carbons, that becomes a ketone, so we get propanone. And if we have a CH on the double bond, that becomes a carboxylic acid, in this case ethanoic acid. So the answer is B. And just one final note, if we have a CH2, if we have a carbon on a double bond with two hydrogens, that will become carbon dioxide and water. It's first oxidized to methanoic acid, which is then eventually oxidized to carbon dioxide and water. So a CH2 becomes CO2 and H2O.